Okay, thank you everyone for coming. I am really happy that you came, and I hope that you will find my topic interesting. So, it's estimation of the tree height using the satellite pictures. And I will tell you why did we even decided to go with this solution, or why we find it interesting, and what are the outcomes. So, why we started working on this? So our clients often came to us with the questions that they would like to estimate the height of the tree using the satellite pictures. And they wanted to know further these details, like how much effort it would take, how precise is it, if it really requires a lot high technology stuff, or it's something simple and easily affordable. So we didn't know answers for these questions. Logically, it was completely a new stuff for us. But we decided to look at it. Mostly because if this would be easy and simple solution that we could really believe in, then it would help to solve many of their needs. They would be able to estimate which trees are in risk on falling down on the power lines or on the railroads. Harvesting companies for the timber would be able to estimate which part of the forest are the best one to take down, because they can get a bigger amount of timber from it. And on the other side, if you want to check the forest health and see if it's growing, so during the reforestation effort, you can estimate how it goes, because if the forest is growing quickly, probably it's fine. But the main question is still this one. So, is it possible to estimate the height of the tree with such a precision, and mostly from the satellites? And how we can do that? So, I will explain you the basic physics that you need to understand understand how to solve this problem. So, the magic words for this lightning talk will be the programmetry and the triangulation. I'm not sure if you ever heard about these terms, but photogrammetry is a science of extracting a 3D information from the photographs that are overlapping. So, if you want to know any spatial dimension of the object on the picture, you need to have at least 2 overlapping pictures from different sides. So look at this small graph behind me. So you can see 2 lines that are looking at the hillside of the mountain. And they are looking from 2 different sides, left and right. And you can see that there are 2 points on the hillside, point A and point B, which are on different places on the hillside. One is lower and one is higher. So when these 2 lines took pictures and compare them, they will logically see different pictures. The point A and point B will be on different places. I suppose this is something that it's not surprising for you, but what may come as a surprise for you is that this displacement of these 2 points will be different. So the point B will be displaced more than the point A. And this displacement is called parallax. So this means that the objects that are closer to the viewer, it can be a point on the hill or myself looking forward you. So everything that is closer to you will appear more displays on different pictures from different sides. And we can measure this. Like if you see on the graph, the parallax for point A is much more smaller than the parallax for point B. And when you can measure this parallax, that is easily because you know these points on the pictures, and you know the position of the observers, because you know when the satellite are very well located, then you can use a simple triangulation formula and you can get the spatial dimensions. So, to understand that this is not such a bulletproof solution, we can look at a third line that is looking at much more steeper mountain. So, okay, I hope that now you can see. And now you can see that there is a point C in a very deep alley, and Alan cannot see it, it's hidden behind the mountain. And the same for the point B, D, and E. They are, you wouldn't be able to see them, because they are covering each other. So we won't be able to estimate the height of these 2 points. So these are one of the problems when we are facing when implementing this solution. And now we can look at how it looks in the real pictures. So here on this slide, you can see two stereo pictures from high-resolution satellite from Maxar. So this is a resolution of 50 centimeters. I think you cannot see much on this slide, but this is the city of Stockholm during winter. And now, these two pictures are different. One is from the right side, the other one is from the left side. We will look at the zoom in later. But we know what is the position and the geometry of the camera of the satellite. So this is something that we can use for calculating. This is simple. But the problem for us is the position of the exact points in the both pictures. So when you look at these two pictures, at first glance you would say that, okay, you can map easily everything. Yeah, because, okay, it's not visible, but there is this tree height, okay, the silka of the trees, and you can map every point from it, like you see it on both of the pictures. But what will come as a problem will be when you look at the side of the buildings. So if you look here, it's not that clearly visible, unfortunately, but this is the side of the building. And this side is not visible here at all, because you have another perspective. So the pixels that are on the side of the buildings, you won't be able to map. So this will be a black dots for which points you cannot estimate the real height. And you can have many points like this, because as I was mentioning before, each point can be covering each another. So I will make some small arrows here, but unfortunately I think you won't be able to see it. But there is another problem that we are facing, and that is that you need to have some solution how we will map these points, because these pixels have over 800 millions of pixels, of points. And you cannot map them manually, right? It doesn't make sense. We want to have an automated solution. So we need to have some algorithm that will be able to create the mask of the points, and they will be searching for the matches between the left and the right pictures. So it won't go point by point, but it will be searching between the similar patterns on the picture. And what is happening is that when we look at the real results, the points that have strong features, as these buildings, they can be mapped pretty easily, because there are strong features. The object detector is able to easily map them, no problem. They are quite strong. But what is happening with the points that are less markant, let's say as the forest, you cannot see any strong features for them, because logically every tree looks similar. So there is not any strong feature that you can see. And this is a depth map, okay? So practically these colors that you can see on the picture on the left side, so they are colored based on the height. The bar in this picture, it was between 0 and 120 meters. Maybe you are thinking why this part in the middle is so high, yeah, compared to the rest, because it should measure a real height, right? Why suddenly there are some buildings that are too high in this picture? So in fact, what is happening is that when you are calculating the height of the object, you have to remember that you need to take into the account the terrain. So the first thing that needs to be very precise is an elevation model of the terrain. That must be really, really precise. This picture, or this elevation map, was already done with like removing the terrain map from it. But due to the fact that the terrain map, the one that I downloaded from, that it's freely available on the internet, it wasn't precise, and this is why the hill that is in the middle, because this is a small hill in the city of Stockholm, is still elevated, because there is still a high difference. So this is another problem in the solution, that it's not only that you need to be able to calculate the height pretty correctly, but you need to have even the basic terrain elevation model that it's done with very high precision. Now we just go to the last slide of the presentation. So this is a living area of the city of Stockholm. And you can see that there are some trees around the buildings. And you can see, oh, sorry, no arrows here. So you can see that the roofs of the buildings were detected pretty easily because they have a strong shapes. But for a forest, you see just the black dots. That doesn't mean that they have a zero height, but that means that they were not mapped because there are no strong features for us. So, what is the outcome of this PPT? Technically, the estimation of the tree height from the satellite picture is possible because there are plenty of mapping algorithms that are able to estimate even, or find the strong features even for the trees and be able to map them. But it requires a very high computational effort, lots of custom algorithmizations, because algorithms for trees are not that available, and moreover, you need to have a very precise elevation terrain model, so you can remove the elevation of the terrain from the elevation of the trees. So that's all of my side.